Hey,
Hello.
how are you?
Hey Shane. How's your week going?
It's going well.
Yeah. When do you usually start like working? At least tutoring.
Yeah, like around now, like or noon.
Got it.
Mhm.
So I'm your do you have one before me or this I'm like the first of the day
First
person?
thing.
Got it. Alrighty. Well, you saw my emails, right? I sent over a couple passages
Hmm.
um in advance.
Hmm.
Um Not sure if you were able to glance over them, but yeah, just guess I wanted to continue today, going over some of the stuff that I've been doing. Because I have not been doing well like in physics.
Hmm.
So here, you see it now?
Um, yeah.
Okay, cool. Okay. Should I read it?
Uh, yeah.
Okay. Radar is a natural method for detecting objects in air, whereas sonar is used to detect objects underwater. Radar is used by bats, which emit sounds that reflect off prey in the environment and return to the bat. During echolocation, the time between the emission of the sound and the return of the sound allows the bat to determine how far away the prey is from the bat. Okay. Um, in in addition to the distance of prey from the bat, some researchers think that radar allows bats to determine the relative speed of their prey. Information regarding the relative speed of prey can be obtained by detecting a Doppler shift in the frequency of sound between when it was emitted and when it was returned. The Doppler equation is this equation describes the relationship between frequency of the sound emitted by the bat, frequency of the sound when it returns to the bat, speed of sound, speed of the prey relative to the bat. Positive value for VT indicates that the bat and the prey are moving close together. Negative value indicates the bat and prey are moving farther apart. Okay. Yeah. As opposed to radar, which is typically used for medical applications, sonar is used in the ocean. Sound waves travel a fixed number of wavelengths. Acoustic intensity I decreases as the sound travels a distance r such that I is proportional to 1 over r squared. It is important to keep in mind that during both sonar and radar, the sound travels to and from the reflector, resulting in a two-way loss.
Okay. So, um, so yeah, why don't you describe to me what echolocation is?
Like the bat basically lets out whatever its echolocations, like emission or whatever. Well, yeah, like there's the emission to sound. The
Hmm.
echolocation is the process of a bat emitting or some sort of organism emitting a sound. They then they're able to see how long it takes for that sound to travel a distance and be reflected the same distance back from whatever it was.
Hmm.
And then they're able to figure out the how far the thing is using time.
Yep. So, because when they shoot out a sound wave which travels at a known speed, like the speed of sound, and it'll hit whatever thing it hits, and it'll then bounce off and then come back. And so they can think like, okay, as I emit the sound, I can think, or I can wait until when it comes back to me, and then I can use the known speed of sound to figure out how far that thing is. Um, so that's the echolocation thing. There's also then the relative speed, which is radar, and then that involves the Doppler effect. And like the key thing about the Doppler effect is that it works for things that are moving. Um, like either the observer or the source is going to be moving. If they're not moving, then you won't get a Doppler shift. And then they talk about the intensity later and how that's inversely proportional to the square of the distance r. Um, and that should make sense in terms of, do you remember what the unit for intensity was?
Uh, no. Wait, like intensity. Well, for light, it's the amount of photons. For sound, it's the amount of sound waves. I don't know.
Yeah. So the unit for it is going to be watts per square meter.
Mhm.
So, in other words, power over area. And so that's why this relationship of intensity being inversely proportional to the square of the distance, that's why it's a squared term and not just a regular, 1 over r, because it's indicating to us an area. So, okay. So it seems like, okay, so for this passage, um, what we want to be aware of is the fact that, okay, they first talk about echolocation and, they're likely going to ask us about that. And then they talk about radar using the Doppler shift. So they're definitely going to ask us something about that. And then they uh, talk about the intensity and how that intensity, they talk about at the end this, well, okay, they talk about radar and then they talk about sonar essentially being the same thing, except it's used in the ocean. Um, and then they talk about the intensity decreasing. And so they, you know, last thing they say is that there's this two-way loss in intensity. Um, oh, and then, so yeah, what you said was correct about the number of like sound waves, but uh, also know that it would correspond to loudness.
Mhm. Yeah, in my head, it's like intensity, amplitude, loudness are all correlated,
Okay.
right? And then pitch and frequency are correlated.
Mm-hmm.
Okay.
Yep. So, okay. So let's see. The waves emitted by submarines tend to have a greater wave speed. Okay, I see what they okay. Then do the waves emitted by bats. Which of the following must be true? So tell me what you're thinking here.
Uh, yeah, one sec. Um, okay, so I mean, if it's a higher wave speed, then I feel like it'd be a higher frequency.
So any equation or anything like that for you to think about?
Well, the Doppler one relates frequency to speed.
Anything like, well, that's, when it's trying to bounce the sound or whatever wave to be like bounce off of like a moving thing. But they're really just saying here that when a submarine does it, it's traveling at a faster speed than when a bat does it. So what's uh what's a more fundamental equation?
V equals F
Uh-huh.
H or V equals F times lambda,
Good. So
or V equals HC over, or no, V equals HC over lambda or E, or V equals HF.
okay, so let's talk about those. So so those the HF, the things with the H in it, can we use that for what they're talking about here?
Sorry, no, it's Planck's constant.
Huh? So any of those equations you mentioned with Planck's constant, would they be like appropriate to use for this type of?
No, because sorry, it's light,
Yeah.
photon based. Okay,
So if this isn't light, what is it?
it's sound.
All right, and what determines the sound, the speed of sound?
Speed of sound is determined by the medium that it travels through.
All right. So and tell me a little bit more, like what type of medium is it?
It is fastest in a solid medium,
Huh?
then liquid, then gas.
All right. Submarines uh have so so we're talking about sound waves and submarines have that sound wave in what medium?
Then liquid medium.
Uh-huh. And what about bats?
Gas.
Yep. So which should travel faster?
It will travel faster in a submarine. Well, coming from submarine in liquid.
Because of the medium that it's in, right?
Yeah.
So that's independent of wavelength or frequency because typically the speed of sound or the speed of whatever wave is the thing that's constant. And so if you increase, wavelength, you're going to have to decrease frequency. If you increase frequency, you're going to have to decrease wavelength. But frequency and wavelength alone don't tell you anything about the speed of the wave.
Mhm.
So this is just trying to trick you because it's not going to be any of these, or rather, it'll be D because it's
Yep.
just medium, right?
Mhm.
So yeah, so remember that the speed is determined by the medium. That's true for light as well. Um, and the denser the medium, the faster. Well, for sound, the denser the medium, the faster it will travel. The sound will travel. For light, it's the opposite. The denser it is, the slower it travels. So yeah, so this is just trying to, I guess, trick you or whatever.
Got it.
Mhm.
Okay, so yeah, I mean, basically, the wave speed just depends purely on the medium.
Correct.
Um, not the frequency. Okay.
Hmm.
Yeah.
Oh, nice. Okay.
Yeah. So here I was a little confused. I mean, I know we're given amplitude, I mean, intensity equals one over R squared.
Hmm.
Um, so it's got to be probably like B or D. That's what I was thinking.
Okay.
My question was, do we would have to include then the distance that it travels and back, right? Or
Hmm.
then it would be D,
Yep. The two-way loss.
right? Okay, that's true. Okay. Body emits a sound to a wave and it's like fucking sound to waves. 2 seconds later. So here, I mean, you have the speed of light, right? That's, oh no, speed of sound. That's 340 meters per second. And you equate that to distance, what we're trying to find. Um, I guess over one, because here, I mean, it's coming 2 seconds later. So it takes 1 second to travel there, 1 second bounces off, and 1 second back, right? So 1 second there bounces off, 1 second back.
Uh, what did you say earlier about okay. So, okay. Now, okay, sorry. Earlier you said the 340 meters per second that you set equal to what?
Yeah, because we equate the speed of sound to distance over time.
Oh, I see what you're doing. Okay. And then to find distance, you would multiply it by time, right?
Yep.
Okay. And then you would get something like 700, right?
Well, that's a bit that's like if we're considering distance there and distance back. But what I'm saying, yeah, I mean you could divide 700 by 2.
Yep.
So it would be V.
Mm-hmm.
Yeah, right.
Mm-hmm.
Okay. Okay, this was pretty tricky. I just did not understand. Um,
So now, okay. So so a sound wave upward so that the wave travels from water into air. What's the significance of that?
so when a wave travels from water into air, it's a different medium.
Which means,
Um, okay, from water into air, it gets slower.
yeah, good. So so remember how we said like V equals wavelength times frequency?
Yeah.
And if the V is held constant, the frequency and wavelength will be inverse. But here, the V is changing, right?
Hmm.
So now only one of, whether it's wavelength or frequency, only one of them will change. So let's think what can change.
I would think it's frequency.
Okay. What?
I mean, it said sound waves travel a fixed number of wavelengths.
Well, what is that? Well, fixed number of wavelengths. What does that mean?
Uh, don't really know, but yeah, I mean, I wasn't really sure to figure this out. I think I figure this out at all. So
Hmm. So let's see. So maybe we can at least, if we don't know if it's frequency that's changing or the wavelength that's changing, we can at least maybe know if it should be like a higher one or a lower one, right?
uh, probably. So I mean, if it's going to air, it's going slower. Um,
So if that decreases, we should see one of these guys decrease or increase.
Decrease.
So if so earlier, if we had the velocity as a constant, then if frequency goes up, wavelength must go down and vice versa, right?
Yep.
But here, velocity is not a constant. So if it goes down on the left, ultimately this will have to go down, right?
Yeah.
So so we should be seeing a like shorter, either a shorter wavelength or a lower frequency, right?
Yeah.
So we can get rid of C because it says longer wavelength and B because it says higher frequency, right?
Yeah.
Okay. Now, the peculiar thing about something is that it does not change when you enter into different mediums or media.
Wait, were you asking me like question?
Oh no. So well, I guess kind of in a way.
Huh?
But
I was waiting for like the,
yeah,
you
yeah.
know,
So there's something that there's a either velocity, frequency, or a wavelength. One of these simply does not change as you enter into different media.
and that's wavelength.
So
Yeah.
we know that the wavelength, so remember like the chromatic dispersion
Yes. Yes.
where you have like white light disperse into all the colors of the rainbow.
Mm-hmm.
So what differentiates colors?
Wavelength.
All right. So we have an example of wavelength changing there, but the frequency is something that does not um, change when you go from one medium to the next.
Okay.
So that's something that you have to know. It's like kind of like a weird reason for it because it's kind of like because it's frequency is like the number of cycles per time. So the time part doesn't really uh or can't really change. So you're not going to have when you enter into a different medium, you're not going to have the frequency change.
Okay. Yeah. Got it.
But
And
links that
this,
I sent in the
I'm looking at it. Okay.
so you could see how when we enter into this new medium that the wavelength clearly decreases, right?
Mhm.
And the frequency is not changing because its velocity is moving slower, right? As so this is for light, so that's why it's going slow, like slower in that denser medium. For sound, it would just be the opposite, but the same principle applies, which means that um, when entering into a new medium, you will have the velocity of the wave change and the wavelength of the wave change, but not the frequency.
So can you then, this is different, but I had a card on this. Can you explain this? So refract, I had a question on this in UWorld a while back.
So this is saying refract more,
Mhm.
but as you have something with a higher frequency, but it doesn't mean that the frequency of anything changes. It's just that, like Roy G. Biv, we know that red has the longer wavelength, thus um, would we could say like would have like a lower frequency, and
Uh-huh.
blue or violet light um, will have a um, higher frequency and smaller wavelength, but it's not like we can take any of these types of light and like increase the frequency of it directly. So what you see in this chromatic aberration due to dispersion, the dispersion is the separation of the incident light, which is going to be white light. I mean, they drew it as like kind of like a rainbow, like even as an incident wave, but I guess technically it's still going to, it can be like that, but yeah, what we're seeing here is the dispersion. So we're separating. Um, so this would be like, I think, easier to conceptualize if you just think about it in terms of wavelength. So violet light has a smaller or shorter wavelength compared to red, and as a result, violet light will refract or bend more. And but yeah, you're still not having any change in frequency. It's just that it's like you can't take violet light and turn it into, let's say, um red light. Yeah. There's no actual change in frequency. It's just that, you know, red light or yeah, red has that lower frequency and violet has that higher frequency.
Okay.
Hmm.
And also, um, is it true that light with a longer frequency is going to refract less when traveling
Hmm.
to a different medium?
Yep.
Oh, there it is. I found it.
It's like this one.
Oh,
Oh, let's see.
oh, okay. Yeah.
Dispersion. Yeah, laser with a longer frequency, sorry, longer wavelength, um, refracts less when passing from air into glass because dispersion causes wavelength dependent refraction. And then let's see, infrared, longer wavelength, less refraction, ultraviolet, shorter wavelength, greater refraction. Um, so yeah, you see that in like the Roy G. Biv example that I drew for you before. Um, you can see that the red is all the way up here, that it has not really refracted much. But
Hmm.
as we go up in frequency or go down in wavelength to like violet, you can see that it's refracted far more. It's bent a lot more.
Wait, violet has the lowest frequent wavelength?
For visible light, yep.
Yeah. Okay.
And red has the highest wavelength.
Yeah.
And so you can see that this is the incident ray, and the red has not really like bent that much compared to the violet, for instance.
Right. Okay.
Mhm.
Okay. Got it. So, anyways, the verdict here is that it's unchanged frequency. Um, right?
Sorry, I was trying to look see if I could find like a simulation or whatever to show you, but
Mm.
oh wait, I don't I don't know why I did that to D, but
Yeah, yeah.
we know we
I got a little scared.
so sorry, so we know that it won't be a longer wavelength and it won't be
Yep.
a higher frequency, right? Because if
Yep.
anything, it should be lower. So, and now if we just use our knowledge of frequency is not something that changes as and go from one medium to the next, and that wavelength is a thing that changes. Yeah, it should be D then.
Okay. Would you show the cross like erase? Yeah. Which of the following would increase the Doppler shift? Um, Doppler has to do with things moving toward one another.
Hmm.
Um,
So you said it'll be higher if they're moving towards each other, right?
yeah, I would say yes. So that would cross out B. Yep.
And
A
then,
stationary.
yep,
C. So that does not have like that doesn't constitute anything with Doppler, right?
yes.
Like,
Remember, how I said Doppler is just for things that are moving. So, because if things are stationary, like the frequency is going to be whatever, you like source frequency will be equal to the observed frequency. The only
mhm,
reason the source frequency can be different from the observed frequency is because something's moving.
mhm.
So the Doppler stuff won't work for things that are stationary. And you can even like, if you did the equation here, the VT is going to be 0. So you're just going to get, V over V, which is the speed of sound, and that will cancel, and FE will be equal to FO. So if they're stationary, Doppler is not going to play a role. Or yeah, there won't be any Doppler shift.
Yep.
Okay. Now, for D, submarine emits a sound wave toward another submarine that's moving in the same direction at the same speed relative to the initial submarine. What are your thoughts there?
Not sure that would do much. Like, wouldn't that just be similar to C?
Tell me how.
Uh, they're both moving in this. They're just moving in the same direction.
Hmm.
So they're both going like neither's going closer to the other.
Yeah, it's like um like they might both be moving, but they're moving at this in the same direction at the same speed, so it's indistinguishable from if they were just stationary.
Yes.
So almost like, Newton's first law there of like Object in constant motion will stay in constant motion unless acted upon by another force, and object at rest will stay at rest unless acted upon by, another a force. Because yeah, and I guess like an easier way to visualize that first law is that you are, let's say you're in an elevator and it's moving at constant speed. Whether it's moving at constant speed or it's not moving at all, there's no way for you to tell if you're in an elevator.
Why? Wait, what?
So like the only way you're able to tell if an elevator is moving is when it has an acceleration. So like when it's stationary to moving, you have a
Okay.
change in velocity, therefore an acceleration. You could feel the acceleration, but past that, like when it's moving at a constant speed and you like don't get to see the outside, there's no way for you to tell whether it's moving at a constant speed or constant velocity or whether it's stationary.
Yeah.
So that's yeah. So D is going to be, as you said, close to C. So yeah, it's going to be, as they move closer toward one another.
Right. Right.
Okay. So there's going to be some definite, I already, just from looking at it, I have a feeling that's going to be something.
Mhm. Okay. An air entrainment valve consists of an open-ended constriction in the tube, altering the velocity and pressure of the fluid in the tube. If the pressure of the fluid is less than that of the gas surrounding it, the surrounding gas will be entrained in to equalize the pressure.
So check this out. So whenever we see Pat, so I think yesterday or 2 days ago, we did a passage on something that involved the buoyant force. And so I was telling you like that stuff should come to mind. So this passage right here, I could see right away that it's fluid stuff, right? So you
Yeah.
want fluid stuff to come up on in your like mental kind of Rolodex or whatever. So you want to be thinking of like, and you'll start to get a good sense for this. Like this over here, you're gonna, we're gonna talk about it, but I mean, that already is something that is related to that. And I haven't even read the question or passage yet, but you want to be thinking of these things when you read this stuff. But
Mhm.
okay, so yeah, an air entrainment valve consists of an open-ended constriction in a tube. Oh, you know what? Even that, I feel like they might, well, maybe not, but what I'm thinking of when I see that is resonance. Um, but that might not be the case. But like harmonic resonance, like open uh
Mhm.
tube, closed tube, something like that. But okay. Altering the velocity and pressure of the fluid in the tube. If the pressure of the fluid is less than than that of the gas surrounding it, the surrounding gas will be entrained to equalize the pressure. Okay. And then air entrainment masks are oxygen therapy devices able to provide inspiratory flow at a specified O2 flow rate. So flow, we want to be thinking about, you know, either like the continuity equation, the Bernoulli uh equation, or like Poiseuille or something like that. Um, and flow, like what unit does flow, like would a flow rate be?
A flow rate would be, I think m cubed per second.
So volume per time, right?
Yeah.
Yeah, good. So, okay. An air entrainment valve is used in the air entrainment mask to decrease the delivered concentration of oxygen, usually in patients who are at risk of dysregulated respiration if given too high oxygen concentrations. When an appropriate flow rate is put through the valve, the surrounding room air will be entrained at an appropriate rate and achieve the desired end oxygen concentration. So, what are they talking about here?
They're basically talking about like delivering oxygen to a person.
Mm-hmm.
Um, but like the way that they designed these, so it's like not too much oxygen is given.
Mm-hmm.
Yeah,
So, what does entrainment mean?
no idea.
Well, I mean, like, it's not something you're expected to know, but from what the passage,
Oh,
how that describes it, yeah.
oh, like controlling the gas to stop sort of equilibrium. Like,
So, the first paragraph, we say that there's an air entrainment valve, which is an open-ended constriction in a tube, and that alters the velocity and pressure of the fluid in the tube. That fluid, would be like oxygen in this case.
mhm,
And that if the pressure of the fluid is less than that of the gas surrounding it, the surrounding gas will be entrained or like enter in to equalize the pressure. Okay. So entrainment is when the pressure of well, in this case, the fluid is that of O2 is less than the gas surrounding it. The gas surrounding it is air, right?
mhm.
Okay. So I now see that the open-ended thing is not going to be about resonance, but it's about this schematic here of this mask. What's happening here? Because there's a lot of stuff that we can figure out from this.
There's some ideal flow and there's some like maybe more turbulent flow.
Well, for turbulent flow, we would see like some type of
Oh, swirly thing.
yes,
Oh, okay.
but compare like I guess point A here to let me like since I already have point B, let's say that compared to point C, what's tell me about that.
There's higher pressure.
So the so the arrows, if they are closer together, it means that they're traveling faster.
Okay.
And if they're traveling faster, what can that mean? Or what other thing may be affected by that?
Area is down.
Oh, sure, sure. Anything else?
Uh,
Because because this is where entrainment happens, and entrainment happens when what happens?
Pressure.
Uh-huh. Pressure of the O2 in this case would be less than the pressure of the air, right?
Hmm.
So we could see that compared to point A, where the field lines are more spread apart, at point C, they're closer together, which means that it's traveling faster. And if it's traveling faster, it's going to have what effect on pressure?
Like pressure is higher.
So let's say that, so okay, sometimes it helps to think about extremes. So let's say that the O2 over here is traveling so fast. Or okay, the other day I was like, this is like my kitchen counter, and like this is my bathroom, and I had like some piece of paper here or something. And I like ran kind of fast to my bathroom, and then the paper kind of like kind of like moved around like that. Now, if I was moving at a slower speed, that would not have happened. So think about that a bit.
Yeah. Okay, I thought about
Okay.
it.
What are you thinking?
Um, I don't know. It's a great question. I never really thought about it. Now that I think about it, I don't know why that happens. I
Oh,
mean, I guess it's like
so
force of air.
in order for this piece of paper to move in this direction, right? It would have to either be pushed by, let's say, some air or pulled in,
Hmm.
right? And there's nothing like on this end to like push it, so it can't be a pushing thing. It must be that it's getting sucked in and moves that way. And if you take this to an extreme, like let's say that I run like so fast that I create a vacuum in this region, it will suck in the piece of paper here.
So that's why in the lungs it sucks in the air, for example, right? It's the pressure differentials. The same thing as here.
So the in the lungs, the pressure differential is caused by a change in volume. Like inhalation is when your diaphragm contracts and your lung thoracic cavity volume increases, which lowers its pressure compared to the outside, and that's why you have inhalation. So that's due to just a change in volume. But this is due to, if my speed is going higher, it's going to create a low pressure region. So, so sorry, I was just seeing if I could find some type of simulation for this, but basically what it is just that if something moves really, if air is moving really fast, so like also like if this is like a window and there's a hurricane outside, um, what you typically see, like if the windows break, is that instead of breaking inwards, they break outwards. And if you can imagine like some like hurricane winds going like this really fast, it creates like a temporary vacuum in this region, which is really just a low pressure region. And things get sucked into lower pressure regions. And so the glass breaks outwards in something like a hurricane.
Right.
So yeah. So you want to think about the fact that the higher the velocity of the like whatever air or you know fluid or whatever, um it leaves behind a lower pressure region, which then can suck in things. So we can see here at point C, it's a higher velocity for the oxygen. And then we have the openings here, right? And that's what they mean by the open-ended thing, I believe. So this is open to the atmosphere. So if the speed, so let's say this is pressure at point A, pressure at point C. If pressure at point A is, or let me also put in velocity at A, velocity at C. So if velocity of A is less than velocity of C, we should have um, pressure of A is greater than pressure at C. Velocity and pressure are inversely proportional. So, so the pressure is smaller at point C. Now, the air coming out here with an atmospheric pressure, like it's going to get sucked in because that atmospheric pressure is larger than, so I could also put P atmosphere is larger than P at point C. So we've created a low pressure area at point C, which means that the atmospheric pressure will get sucked in. Mhm. So that's what is happening here. And that's the Venturi effect. Um, I used to like describe it by taking like a straw wrapper because it's like a thin paper wrapper and kind of positioning it like this and then blowing underneath it. And when you do that, do you expect this part to go up or down?
Uh,
So it'll actually go down because if I'm blowing underneath it, the air, let's just say that, it's held together, whoops, by these air molecules. The air molecules get moved out of this region, creating a region of lower amount of air molecules. So this sucks it in, sucks it downwards. So this entire thing will go down.
but so what is the difference between also like with B, right? Poisson flow, that's um ideal flow,
So
laminar.
so yeah, so basically for the um ideal fluids uh can be defined as fluids um that don't have viscosity. Once you introduce viscosity, you're starting to get into the real fluid realm, and that's where you'll see the Poisson flow or the Poisson like equation. So
So my question, like follow-up was like for Poisson flow, that's for turbulent flow, and that's the equation pi r to the fourth over 8 ml,
yeah.
right?
Mhm.
And then for laminar flow or like ideal flow, do we use the equation P plus density GH plus density V squared? Or do we use Q equals AB? Because those three equations are a little like, you know, I don't
So
know which.
yeah, so for ideal fluids, you could use the continuity equation to figure out um, volumetric flow if you have area and velocity. And you can also use if you need more information than just flow rate, like, kinetic energy, potential energy, etc. That's when you can use Bernoulli's equation. Uh,
Okay.
and then for, yeah, so that would be for that. And yeah, the idea, oh, maybe this, let me try this on.
Yeah, I see it. It's moving back.
No, wait,
Yep. Yeah, it's like moving toward you. Yeah.
yeah, I'm doing it wrong. I'm doing it wrong. Maybe it's the length of this. That's right. Okay. Going this way, right?
Hmm.
There you go. So I'm blowing over it, and this is moving up.
Yeah, because you're blowing away the air molecules that creates the vacuum.
Yep. So I'm creating, so the air velocity is faster above it, which means that this pressure region above it is smaller, and so this gets pulled up.
Hmm.
Yeah. I'm glad that worked because I'm always trying to like this is always something that's kind of hard to
Hmm.
conceptualize. So right away, that's what we have happening here. And there's I've seen more than one question about this type of oxygen kind of thing, mask or whatever. And when you see that, just think Venturi effect. But okay, cool.
Wait, but to finish, we're the train of thought, like
Uh-huh.
you're saying that for turbulent flow, you can use the continuity equation and uh
Oh,
the
sorry.
other one.
So continuity equation and Bernoulli can both be used for ideal fluids. Ideal fluids are defined essentially are defined as, not having a viscosity.
Hmm.
But once you introduce viscosity into the equation, literally, um, you're dealing with real fluids and they will exhibit Poisson flow, in which you would see things like, um, so like if the arrows are equal, it'll be like ideal laminar flow. But if they're like bowed like this,
Hmm.
that's Poisson flow because the fluid that's closer to like the walls of the container like have friction against those walls. And so it gives you that bowed shape rather than a flat kind of shape. So yeah, so that's Poisson flow. And now turbulence is just when you have, a whirlpool type situation. And that's also something that happens with real fluids. Um, and it's related to something called the Reynolds number, which is actually inversely proportional to viscosity. I mean, so is Poisson flow actually, um, because viscosity makes it harder for like the whirlpools to happen. But But okay, so we see this and we see that this lets the air come in and you see it mixed over here. So okay, awesome. So let's see. The patient's peak inspiratory flow may exceed the flow rate of the O2 air mixture exiting the air entrainment valve. To compensate for this, so we have that word compensate, so it's going to do something to make it so that we solve the issue that comes with exceeding the flow rate. So to compensate for this, a higher required inspiratory flow rate is obtained by in training additional air around the mask. A researcher was concerned that this will dilute the final delivered oxygen concentration below what is acceptable for a patient. A researcher investigated the effect of manipulating the O2 flow rate at point A in figure 1 on the mixed O2 air flow rate at point B. This data is collected in table 1. So let's see. So flow rate at A, it's in liters per minute. And then for the B, it's 45. And when it's 6, it's 68. Okay. And then if it's yellow, it's 45, blah, blah, blah. So yeah, okay. They'll if they ask us a question about that, they'll have to give us like, some value, like to be like, okay, you can't dilute it beyond, something. And then we can figure out what type of valve and stuff that is.
Mhm.
So when you see these passages, those are the things I want you to be like kind of thinking of. Um, and especially like oxygen kind of this type of mask. So, which of the following concepts explain why air is entrapped into pure oxygen in an air entrainment mask? It's definitely going to be your what is it? Your Venturi effect.
Mhm. And it's not it's not the seal flow because um we're just I mean it doesn't explain it, right? But also here this is like a is this an ideal fluid or no?
Um, so uh so the question is, it's asking us what is the reason why air gets, entrapped. So it doesn't even really matter if it's ideal or not here because the phenomenon they're asking about is why does the air get sucked in?
Mhm. Okay. Okay. Okay.
Yep.
Okay. Hello?
Mm-hmm.
Based on table one, what is the effect of increasing the flow rate of pure oxygen in an air entrainment valve? Um, liters per minute increases when O2 per air mix. Okay.
Okay. Based on table one, what is the effect of increasing flow rate of pure oxygen through an air entrainment valve? Um, okay.
I would eliminate B and I would eliminate D.
Which ones?
B and D.
Why?
Because there's some sort of change.
Oh, well, tell me more.
If you look at the table at point B, there's a higher liter per minute when O2 and air mix.
Mm-hmm.
So B it's just saying an unchanged volume of air, and then D unchanged concentration of oxygen.
Okay. So, B, unchanged volume of the surrounding air is inspired. So they're asking us what. So I think, yeah, I think you're. So yeah, they're asking us if we increase the A, if oops, if we increase this, what effect would that have?
Oh, that was asking to compare A and B. Yeah.
So, so yeah, if you increase the O2 flow rate, what effect would that have?
Good.
So,
Um,
I guess we can, yeah.
well, it would yeah, I don't know.
Hmm. So, okay, let's look at each of the choices. So A says a reduced volume of surrounding air is inspired. What um what is that saying?
That there's just less air from like the out open. There'd be less open air coming in.
Okay.
I mean, if you increase the volume, the velocity, that would decrease like the pressure.
You said if you increase the velocity?
Yeah, because if you increase the flow rate, if you increase, right?
Uh, okay, let's see. So let's see what we first noticed. So we see that this going up that way increases that. This going up increases that. That going up increases that. That going up increases that. So we should see a higher. flow rate at point B, and point B is when we have um I guess the mixture here. So let's see, a reduced volume of surrounding. Okay, if you increase the flow rate, a reduced volume of surrounding air is inspired. Okay. We should have maybe an increased volume of surrounding air that is inspired, right?
Why?
Because we know that, I mean, two reasons. One, Venturi effect, the faster this goes, the more of the air that gets sucked in. But also from the table, we know that if whenever we increase our flow rate of pure oxygen, aka point A, like from 4 to 6, from 6 to 10, etc., the flow rate of the oxygen air mixture goes up. And
Mhm.
that means that, that we are introducing air into it. So that should be a increased volume of surrounding air that's inspired, right?
Yeah.
So, so that would work if it was, well, if it's at a higher volume of surrounding air. So, and then let's look at B, an unchanged volume of surrounding air. What do you think about that?
Probably wrong. We
Yeah,
just discussed it'd be higher.
exactly. So A and B are out. Then C, inspired air contains a lower concentration of oxygen.
Uh, Maybe.
Okay.
Um,
Yeah.
I mean, like we're taking in air, so like I don't know what that air is, whether it's oxygen, nitrogen, or whatever, but it would lead to lower concentration of oxygen in point A.
Okay. So let's see. If we are increasing the flow rate of the O2 air mixture, um, that should cause um okay, and we also talked about the let's see, if the patient's peak inspiratory flow rate exceeds the flow rate of the O2 air mixture, compensate for that, higher required inspiratory flow is obtained by entraining additional air around the mask. And, and then the guy was concerned that this would dilute the final delivered oxygen. And so they collected the data and stuff like that. So it seems like if the flow rate of the pure oxygen increases, that the flow rate of the oxygen air mix increases. And so, okay. I mean, so we know he was concerned about the dilution and that he conducted some, he manipulated the O2 flow rate and investigated the mixed O2 air flow rate at point B. And he saw that the flow rate just, it got increased for the O2 air mixture. So, and then after the point B, we'll enter into the person's, body. So that's inspired air. So would it necessarily mean that it would be a lower concentration of the oxygen? Um, it could be easy to think that because if we're mixing it with air, it would have, relatively speaking, I guess, a lower concentration of the oxygen, but we are decreasing the pressure, which and for gases, like the partial pressure is proportional to the concentration. So I think that we're yeah. So I think, the fact that he conducted this study to see if it would dilute the final oxygen concentration. And although it doesn't really tell us explicitly if it does that or not, um, I think the fact that as point A increases, point B increases to make up. Let's actually even see if it's so like from 4 to 6, or maybe like 12 to 20, it's almost twice as much. 24 to 40 is also almost twice as much. From 8 to 12, it goes up by 4, which is it goes up by 50%, right? And then 33 plus half of 33, which is like 15 or 16 rather. Um, so okay, I think this also goes up by 50%. Um, the 33 plus the 16, right? So it seems like the flow rate is kind of compensating for, right? So this one's tricky, like between C and D. Um, but I think that the fact that the point B flow rate increases means that you won't dilute that um, oxygen concentration because we're having an increase in the flow rate, in the volumetric flow rate, and it's of the same proportion that we change the flow rate at point A.
Hmm.
So I think it should be this.
Yeah, it is because it's compensating, you're saying?
Uh-huh. So the issue that we have in this paragraph is that the patient's inspiratory flow rate, which we don't have here, like point A, point B. I guess point B is closer to where the patient's mouth would be, but that's the inhalation like flow rate, like the volume of the air O2 mixture that a person can inhale per unit time. So we know that if the inspiratory flow rate is higher than the flow rate of the O2 air mixture at point B, that that they're not going to be able to make use of it because they're sucking it in at a larger rate. And so to compensate for this, they added the air, you know, around the mask, which increases that volumetric flow because you're adding volume by adding air. So that's what that was made to compensate for. And then the researcher's concern about this diluting it, um, is the reason that he did this experiment. And it's a little tricky because they're not really telling us what the conclusion was of this experiment. So, but what I see is that we essentially have a proportional increase of flow rate at point A and at point B. And if we have, a proportional flow rate, it should not really change the concentration of anything. Because like, okay, let me describe it like this. Let's say that this stayed 45. Okay.
Yeah.
When you increase the flow rate of pure oxygen, the oxygen O2, the oxygen air mixture remains at a flow rate of 45. That means that you are not changing the flow rate, but that means that we are getting the same flow rate, but O2 and air, and that would mean that you're going to get less O2. That would be the situation where you would have a lower concentration of oxygen. But since the flow rate of B increases proportionately to the one at point A, it means that the O2 concentration does not change because we're increasing that flow rate
Yeah.
to match that, right?
Okay.
So yeah, this should be an unchanged concentration of oxygen, but this was a really tough one. But we could at least bring it down to C and D at least.
Mhm.
Um, okay. So this is like, you know, a question that we could even answer without the passage because we could just use units. Okay.
Yeah.
So they're asking which of the following when you multiply by the volume flow rate, what's the volume flow rate unit?
M cubed over S.
Yep. So I'll just write volume over time. What about power?
Work over time.
And do you remember what work could also be equal to?
Joules.
Yeah, energy, right?
Yeah.
Energy over time. So, um, so now, I mean, the time part is the same, but now let's think about what makes energy different from volume. So, like, volume, we can say is like, let's say a cubic meter. Um, what about energy?
Um, Newtons times distance, like meters.
Uh-huh. And deconstruct units for newtons.
Uh, it's kg times m cubed. Sorry, kg times m over second squared. Yeah.
Good. Um, and that's the Newton part. And if you multiply it by the the meters part, you'll then get that, right?
Yeah.
Okay. So, um, so you would have to multiply it by, so like this times, let's just say X equals, um, cubic meters.
Yeah.
And, oh, wait, it's the other way around. Whoops. So it's the, cubic meters over time multiplied by, let's say, X is equal to the energy. Oh, let me put that over seconds. Well, I guess that will just turn into seconds cubed, right?
Mhm.
So what can we um, multiply this by to get that?
Uh, kg times s squared over m.
Um, so if we do x is equal to,
Equal
yeah,
kg times um just kg over m times s squared.
kg times m.
No, kg over m times s squared. Kg over like m times s squared. Yeah.
Okay, so good, good, good. Um, okay, so all right, let's see. So pressure gradient, what can that be?
Delta P. I mean, pressure is force over area, n over m squared.
And so that's kilogram times meters per second squared, um, over m squared, or rather, yeah, over m squared. So that should just give you kilograms times, or rather, kilograms times meters seconds, I believe. Newtons is this over meters squared. Gonna give you, oh wait,
It's our answer. It's kg over m times s squared.
I'm gonna do it like, oh, by multiplying the reciprocal. So then this gives me kg over mass squared times s squared. No, no, no. This cancels and that cancels. Just m. Okay, wait, that works.
It's our answer, yeah.
M s squared. Yeah. If it was just length of a pipe, like volume over time times length of a pipe, that's like cubic meter over second, let's say, times length, it'll give you like m to the fourth power, like meters to the fourth
Yeah.
power. That's out. Kinetic energy, that's just, I mean, volume over time times energy is just going to give you, it's not going to give you energy over time, right?
Hmm.
And then velocity is also not going to give that to you. So yeah, so that's how you do this type of problem.
Okay.
And you can see like the units are what makes it so that you can answer it. Yep. Oh yeah. These types of questions are common in physics. So, okay, researchers create an air entrainment valve in which the diameter of the valve is doubled. Okay, now I have a feeling of I know what you may have chosen here, but tell me what you're doing here.
So here um the relationship is AV equals AV, diameter is doubled. I mean, when we're finding an area of something, it's the area, in this case, like a circle.
So,
Um, hmm?
so sorry. So if you double a diameter, what would that effect would that have on the area?
I mean, usually use radius. But like if you
Oh,
double, if you double the diameter doubles the radius, area is gonna be two squared, so it's gonna be quadrupled.
good. So, um, and yeah, you mentioned stuff about diameter and radius and circle and stuff, but area is always going to be in two dimensions, meaning like square meter, square foot, right?
Hmm.
So remember that, and remember volume is always going to be in three dimensions.
Hmm.
So so here they're saying that, and I've seen this type of question all the time because people usually equate something like diameter to area. but it's really like the square of diameter, right? So if we double the diameter, that makes the area quadrupled, right?
Hmm.
And the velocity is going to be inverse to that. So this should be decreased by a factor of 4.
Okay, got it.
Did you choose? Yeah.
Um, no, I chose A. Just I don't know why I chose A.
Oh, okay.
Just
So you got you didn't
yeah.
fall for the trap of
No. I mean, I kind of saw a trap coming already. I feel like
uh-huh.
I've done these decent amount where like yeah. But I guess I just forgot about the fact that's an inverse relationship.
Yep.
So
Hmm.
okay, last one.
Okay. Oxygen flowing into a pure oxygen chamber of the air entrainment valve has an initial. Okay, so they're giving us values here. Initial velocity of 5 meters per second and pressure of. Okay, now they're giving us pressure, so this is going to be probably Bernoulli. Um, at the narrow end of the pure oxygen chamber, the oxygen has a pressure of 9 kilopascals. So that's like this is a narrow portion here, right?
Mhm.
And you can see the lines are closer together, which means that they're moving faster. And now we know that, if it's moving faster, it's going to have a lower pressure. So it makes sense that we have the lower pressure here of 9. And then assume that oxygen is incompressible. Okay. Um, and has a negligible change in fluid height, also indicating Bernoulli. What is the approximate velocity at the narrow end of the pure oxygen chamber? And they're giving us the density of oxygen. So again, that's a clue for Bernoulli, right?
Mhm.
Do you remember Bernoulli's equation?
Yeah, P1 plus density times GH plus density times P squared equals same thing, but like two P2.
Do you remember how we derived that?
Uh, from the conservation of all the energy
Yep.
things. So like,
The conservation of energy divided by volume.
mhm.
Okay. So what are some stuff we can
Well,
do?
in this case, would because there's a negligible change in fluid height, would we just remove the PGH?
Yep.
Okay. P1 is 10, and then P is 1.28. Well, density 1.28. Uh, on the left, it'll be 1.28 times 5 squared.
Okay. Let's make sure that we have, okay, kilopascals, and kilograms per cubic meter, and V1 is 5 meters per second, and we just need to find the V2 here.
Yeah.
So I would, uh, so like, would you just plug stuff in at this point, or would you, like, what I would do is I would rearrange it algebraically to solve for V2, and then I would plug in the values.
Okay.
And also remember to take into account the units because the kilopascals is gonna have to change. So we can have P1 plus rho V1 squared minus P2 is equal to rho V2 squared. I can just divide rho to get V2 squared. and then I would just take the square root of this. So then, and now I would plug it in. So the 10 kilopascals I can write as 10 times or 10 E3 pascals. Now, deconstruct a pascal for me.
It's n over m squared.
Good. And we want that because we're multiplying it by something with m cubed as a denominator, right?
Hmm.
So we definitely want to make, yeah. So then we can do 10 E3 pascals plus rho. So this is the 1.28 um, kilograms per cubic meter times the 5 meters per second squared minus the, oh, I guess I could have just done like 10 minus 9,
9.
1, and then 1e um,
So yeah, we could just erase the 10, put 1.
over the, oh, I could have even done the row thing. So I'll just do, so this is yeah, P1 minus P2 divided by rho plus, and I divided the row of the row V1 squared to just get V1 squared, which is the 25. Um, and this can then be 1E3 over like 1.3. So that could be like, oh crap, I forgot the 1/2. So, okay, so we can get the, mm,
Because you forgot to multiply v squared times 1/2. right? Or like originally, because you multiply 25 to 1/2, there's also 1/2 PV squared, like the second velocity. So I'm trying. Because then it'd be v squared equals 2000. You know what I mean? It
Mhm.
would be,
Oh yeah, there's also yeah 1/2 on that side.
and also, yeah. Okay.
So I could multiply this, that cancels, and this times 2. So this is going to be the 2000 over the 1.28, which I'm just going to
Yeah.
2000. And then I just add the 25.
Okay. Yeah, I mean, I get it. Like, I get it. The main thing was Bernoulli. I completely missed that. Um, so now I know.
Hmm.
Yeah,
So
we don't have to finish it, but I mean, we could, but like, yeah.
yeah, so it should be so less than 2000 squared. Um, so 8 squared is 6. Okay, I think it'll be
See, yep.
the only one. Yeah.
Okay.
Oh, okay. So yeah, when you see this, you got it. You just look at. So first of all, whenever you see a, a passage like this, be ready for the things that they'll likely ask you. And things that should be coming up in your head are things like we talked about: continuity, Bernoulli, Basile, Venturi effect, and then for this problem in particular, we have an initial velocity value, a pressure value. So what, equation would include those?
Yeah.
Either Bernoulli or, Basile. Um, but then we are also given this negligible fluid height. So yeah, that's what you're going to be using here.
Okay.
Mhm.
All right. Anyways, I'm gonna go, but
Am
I
I
will
am I seeing you at
6:30. Yeah.
okay.
So just keep in mind the amount of time.
Sure.
All right.
Yeah. Okay then. I will see you
Yeah.
then, okay?
Sounds good.
Take
Bye.
care.